Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library. And I have a great story to tell you. What are our bodies and the physical world around us made of? This is what we're going to take a look at tonight. I would like to take you on a new exploration journey. Through various stories until now, we have explored what we know of the cosmos. We went to space and traveled on a scale that makes us humans feel tiny, almost insignificant. The range of scales in the universe is mind-blowing. But we are also giants, made of thousands of billions of living cells. Each of our cells contains billions and billions of atoms. And atoms contain smaller particles that are tiny in comparison with the space they occupy, and are made of even smaller components. The scales of the infinitely small are as difficult to imagine as the immense expanse of the universe. And this is where I'll take you tonight. So we're going to dig deeper and deeper from our scale towards smaller and smaller levels to better understand what matter is actually made of. We will explore living cells and how they work, complex molecules such as DNA, simpler molecules, atoms and particles down to the scale of quantum mechanics. But don't worry if this sounds complicated. As always, you won't need any particular knowledge of microbiology or physics to understand what follows. It is all going to be simple and logical, as long as you let the sound of my voice guide you along the way. But first, I would like to take a few seconds of your time to let you know that we have a Patreon page for those who wish to and can support this project. Get more of it and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. Our least expensive tier is $3.50 per month, but it doesn't mean you will get less. We let people contribute what they wish or can, and everyone gets everything that is on our page, because the world is a better place when the sun shines for everyone. If you join, you will gain access to various new features. For example, you will have the option to listen to all episodes with or without background sounds. You will have the capability to download all these audios and participate in selecting future topics. We also offer advanced releases and updates on upcoming episodes. There are 20 stories only available to our patrons to date, and we add a new one every month. We have added a link to Patreon as well as links to different streaming options in the description of the episode. But before we begin, let's take a moment together to prepare for our journey ahead. If you'd like, gently close your eyes and let your daily concerns drift away. Find a position that feels natural and cozy. Perhaps make small adjustments until you're perfectly comfortable. Now draw in a deep, nourishing breath, and as you release it, do it softly. Notice how your body responds. Feel the warmth flowing from your neck down through your shoulders, melting away any tension. Let your facial muscles become soft, your jaw loose, your fingers naturally open, and your legs completely at ease. As you settle into this peaceful state, my voice will be your gentle companion as we begin our exploration together. We are going to move slowly but surely, and you may be surprised at how much information we can go through in 1 hour or so when we don't rush and maintain a receptive state of mind and a relaxed body. So, what is matter? This is a trickier question than it seems, because a possible answer to the question is that matter is a substance the physical universe is made of. It takes up space by having volume and it has mass. This is how matter is defined in chemistry or in classical physics, and it matches our perception in everyday life. We are surrounded by matter, objects that can be touched, furniture, walls, vehicles, all sorts of accessories and devices. We know we breathe in an atmosphere made of gas, which is just less dense matter. And from water to air to nature, everything that physically surrounds us is matter. As you know, the little bricks this matter is made of are called atoms. But it could be more complicated than that, because the atomic scale is far from being the smallest that we know of. We'll see later in our exploration that atoms are a combination of particles, which themselves are made of even smaller components. Don't think too much about this yet, but we'll see that these components can be massless and not have any size, which defies our perception of what the physical world is made of. There are particles like photons, the particles of light, which exist without having any mass. There are waves too, like sound, which are phenomena. They are very much a part of the physical world, but they are not matter. Except that we'll see at the end of the story that the tiny constituents of matter can behave like waves. This means that matter is actually hard to define once and for all. Its definition depends a lot on which scale we position ourselves, and several levels, several scales are possible. We are going to dig into this, starting from the everyday usage, which defines matter as atoms and anything made up of them. And then we will dig deeper at various subatomic levels and discover a world where the laws of physics diverge greatly from what we are accustomed to. I mentioned at the beginning that we would explore what we are made of. So our first step in our journey to the infinitely small is going to be the cell. Cells are the basic biological units of all known living organisms. The basic understanding of the architecture of living organisms dates back to the 17th century, which is also the century when the first modern microscopes were invented. Prior to that, there were lenses to magnify things. They appeared in antiquity. But in the Middle Ages, in the 13th century, simple microscopes that were just magnifying glasses were invented. And this is when the exploration of the microscopic world really began. These very basic microscopes were far from powerful enough to see things at the cellular level. To be able to see even smaller things, compound microscopes were invented in the 17th century. They combined a lens near the specimen observed and an eyepiece to view a real image. They were perfected throughout the century, adding better lighting in particular, and by the end of it, the first discoveries in microbiology took place. The existence of blood cells and the first descriptions of living tissues. In biology, the concept of tissue was introduced 2 centuries ago, when it was understood that organs, internal like our heart or lungs or our brains, or external like skin, were not entities in themselves with the same cellular structure repeated over and over. They were made of different types of structures called tissues that carry out a specific function. In the bodies of animals in biology, which includes human beings, some tissues protect an organ from the outside. They cover its surface and act as a barrier. There are also connective tissues that are found in between other tissues everywhere in the body. They support and protect it. For example, they include collagenous fibers that bind bones and other tissues together, and elastic fibers that allow our lungs to recoil. We also have muscular tissue that can contract to produce force and motion, and nervous tissue that is the main component of the nervous system. Without exception, all these tissues are made of cells with different sizes and properties that work together. However, living cells are also highly diverse. On Earth, there are two main types of cells, the oldest of which are called prokaryotes. These cells are the most ancient forms of life that we know of on Earth, and some of them found fossilized were dated to 3.5 billion years ago. Prokaryotes do not bond to form large multicellular organisms. They are unicellular beings. Bacteria are prokaryotes, for example, and their cell is quite different from the ones that constitute our bodies. There are various shapes of prokaryotic cells. They can be spherical or ovoid. In that case, they are called cocci. They can be cylindrical, bacilli, or spiral, called spirala. And there are more. But there is always one single cell in these organisms with a wall, an outer covering that protects the cell and gives it shape. Then there is a membrane that regulates the flow of substance in and out of the cell. And inside, there is a part called cytoplasm. This is a gel-like substance in which various components are enclosed. There are compounds to assimilate organic molecules called enzymes. Enzymes are biological catalysts. They accelerate chemical reactions, and the cell uses these chemical reactions to convert organic molecules into different molecules. This process liberates energy that the cell can use and the building blocks. other part of the cytoplasm that takes up a lot of space within the cell is called the nucleoid. It is the region of the cell that contains its genetic material, DNA. We'll see a bit further what DNA actually is. Prokaryotes are very small, obviously, to our scale, but they are giants if we start counting the atoms and molecules they contain. They have millions of molecules. I mentioned there were two types of cells. Prokaryotes are one type. The other is eukaryotes, which are the building blocks of all plants, animals, or fungi. Eukaryotes are more complex and a lot bigger. They can be as much as 1,000 times greater in volume than prokaryotes. It is believed, based on fossil records, that eukaryotes appeared after prokaryotes. And it makes sense if we take into account the difference in size and complexity. But there is still an open debate today about whether the existing prokaryotes in our environment are directly descendant from the first prokaryote, or whether they re-evolved from eukaryotic cells. In any case, the main difference between the two types, apart from the size, is that eukaryotes have compartments inside. Specific activities take place in different compartments of the cell. One of these compartments is the cell's nucleus. Instead of occupying a region of the cell in which it floats inside the cytoplasm, like in prokaryotes, the genetic material is enclosed in a nucleus in eukaryotes and separate from the rest for the most part, because there are also other small compartments called mitochondria that also contain some DNA, but not chromosomes. We'll come back to the distinction later. However small, a eukaryote may contain billions and billions of molecules. It's a small world in itself. Eukaryotic cells also contain big molecular machines called ribosomes that perform syntheses of other molecules. In plants and algae, they have compartments that perform photosyntheses and can capture the energy from sunlight. And contrary to prokaryotes, they have the property to form colonies or multicellular organisms with specialized cells. Every single second in our bodies, even when we stay still or when we're asleep, billions of chemical and mechanical reactions in our cells are taking place, ensuring that our organisms stay biologically alive. Cells move, they repair, they transport, and they multiply. They replicate. This is where DNA matters. New cells appear by division. One single mother cell divides into two daughter cells, which are copies of the original one. This is what allows growth in multicellular organisms like us, and also the replacement of cells when they die. Human cells, for example, are specialized because we are complex organisms and they have very different lifespans. White blood cells live for only a few days and need to be replaced quickly. Skin cells in the top layer of our skin live about a month. Red blood cells that transport oxygen live about 4 months. Liver cells, 18 months. And there are some, like in the middle of our eye lenses, that last our entire life. On average, the cells in our bodies are entirely replaced every 7 to 10 years. That's fascinating because when you meet someone again after several years apart, you're talking to the same person, yet 99% of the stack of matter in front of you has changed. It's been renewed. It's still the same individual with the same consciousness, memories, and history. Believers would say the same soul. And biologically, it's the same organism. But the matter itself has been almost entirely replaced. Replicating a cell, and for multicellular organisms, coding the entire architecture of the body with its parts, its functions, and how they interact, this requires information. This is where DNA matters. Genetic information. DNA is a molecule, but a very big one. These very large and complex molecules are called macromolecules. Under the microscope, it looks like a double helix, two spirals that coil around each other and contain genetic instructions for the development, functioning, and reproduction of all known organisms. The process is very complex, but a comparison could be made with binary language like the one used in computers, except instead of having two signals, 0 and 1, there are 4. The DNA molecule is a long sequence of building blocks that come in 4 different types, known by the letters A, T, C, and G. Instead of using electrical signals as in electronics, it is through chemical reactions that this information is put to use. Certain proteins will bond with DNA, and they will react to the sequence of building blocks. This is how they read the information enclosed in the DNA sequence. The concept is fairly simple. Protein molecules are attracted to the DNA, and they read and interact with the nearby sequence. It is biochemistry, but in practice, these interactions are extraordinarily complex. The DNA sequence is very long because it contains a lot of information. The process involves many different chemical reactions, and the complexity of what happens all the time in a single cell around DNA is mind-blowing. And to make things even more complex, there is also a bit of simpler DNA outside the nucleus in these compartments, called mitochondria, that also interact with molecules within the cell. What we call a chromosome is one DNA molecule, because there are several in each cell. Their number varies between species, be they of plants or animals. Humans have 46 chromosomes. Cats have 38. Dogs 78. It is not necessarily an indicator of the complexity of the organism. For example, a goldfish has 100 chromosomes. In the DNA molecule, the two spiral chains of atoms that coil around each other are identical. They have the same structure and they carry the same information. When a cell divides, this is a process called mitosis. DNA replicates itself. The instructions to do that are part of the information it carries. A second nucleus appears and separates from the original one, dividing the cell in two. After that, each new cell grows until it becomes as large as the original mother cell, and genetically, they are exact copies of it. But DNA also contains the information needed to make different types of cells, especially in multicellular organisms, where cells become specialized. An embryo begins as a single cell. In the case of sexual reproduction, this cell contains genetic material from two individuals, and the combination of that information is unique to the new organism. This cell divides into two, then 4, then 8, then 16, and so on. And along the embryo's growth process, the activation of information coded in DNA makes new types of cells appear. They form specialized tissues and organs, following an architecture that is also encrypted, coded into the chromosomes. Between the initial cell and a human body at birth, the size of the organisms increases by billions upon billions. But all the information required for this was already enclosed inside the very first cell. There would be many more things to say about microbiology, and maybe we will return to this in another story. But for now, let's continue our exploration of what we are made of and jump to another level. We saw that tissues were made of billions of cells, which are made of billions of molecules. So let's take a look at the molecular and atomic level. You know what atoms are. They are the smallest unit that defines an element. And as you also know, they contain various particles: protons, neutrons, electrons. In nature, atoms often have a tendency to regroup with other atoms of the same type or different. I have referred a lot to molecules until now. Molecules are one such form of grouping between atoms. But they are not the only one. Molecules are very abundant in our biosphere. They make up most of the oceans, the atmosphere, our bodies, and organic substances in general. They are also common near the surface of other planets in space. But it doesn't mean the appearance of molecules is a rule. It depends on the types of atoms and on the environment. Actually, the majority of solid substances on Earth, and that includes most of the minerals that make up the planet, from the crust to the core, are not made of identifiable molecules. To understand how all this works, we need to talk about atoms and something called electric charge. You are certainly familiar with the structure of atoms. They are composed of a nucleus and one or more electrons bound to it. The nucleus is an aggregate of two kinds of particles, protons and neutrons. Protons and neutrons are much more massive than electrons. More than 99.9% of the mass of an atom is in the nucleus. And as you also know, electrons and protons are said to be electrically charged. Protons have a positive electric charge and electrons a negative one. Neutrons have no charge. When an atom has the same number of protons and electrons, then it is electrically neutral. If an atom has more protons than electrons or fewer, then it has an overall positive or negative charge. These atoms with an overall electric charge are what is called ions. But what is electric charge? It can be confusing because the word electric makes us think of electric current, electric power, and electric current is related to this. As you know, what we call electricity, the energy that powers a lot of devices, is a flow of matter, a flow of particles, electrons generally, but not always. And this flow moves from one point to another. These particles in motion energize equipment from light bulbs to computers, motors, radiators. All the electric appliances we use transform the energy from electric current into light or heat or motion. But electric current exists because of electric charge. So forget what we call electricity and think of it as a fundamental property of matter. Electric charge and electric current can be compared with mass and gravitation. As you know, all objects in the universe that have mass attract each other. The force is called gravitation, and it is the force that keeps galaxies and star systems together, or that gives us weight when we are on Earth. Because the planet's mass attracts us, attracts our bodies. Electric charge is another fundamental property of matter. It is a notion, like mass, that explains physical phenomena, except that mass is always positive, while electric charge can have two forms. They are called positive and negative because they are opposed. When two objects with both positive or both negative overall charge are close, they tend to repel each other, whereas they will attract each other if their charges are opposite. This is the phenomenon called electromagnetism. Let's take a concrete example that we experience every day. For example, when we turn on the light, electric current happens between 2 points because one has an excess of electrons. It is negatively charged, and another has a deficit. It is positively charged. If there is a bridge between these 2 points, such as a wire through which electrons can move easily, the difference in potential between them will tend to even out. Electrons will move from one point to the other, and their motion is the force that powers the light bulb. When the light is switched off, the bridge, the circuit is cut off. Current cannot materialize. When you push a button to turn on the light or to turn on any electric appliance, what you do is move a little piece inside that closes the circuit and lets the electrons flow. Of course, for electricity to keep flowing, it is necessary to maintain a constant difference in potential, which is what a power plant or a battery does. So, like gravitation, electromagnetism is the force or the interaction that results from electric charge. It is one of the fundamental interactions that we know of, and that cannot be reduced to more basic interactions. It just exists as a fundamental property of matter. You may have heard of the four fundamental interactions or the four fundamental forces of physics. Gravitation and electromagnetism are two of them. They are the most obvious because they produce effects that can be seen directly in everyday life. There are two more that produce forces at a much smaller scale inside atoms. They are called the strong and the weak interactions. We will come back to them later when we explore inside atoms. Maybe there are more than four. Some scientists suppose that maybe a fifth force might exist. Or perhaps there are four manifestations of another thing, another reality, something else that we don't understand at this point or are unable to define. These four fundamental interactions are not laws set in stone, but in the current state of physics, they have been researched and quantified, and they work. They help make predictions about the behavior of matter, and these predictions have been verified from very large-scale objects like galaxies to much smaller scales like inside atoms. So I was telling you about electric charge to explain the formation of molecules. Around the nucleus, electrons revolved at high speed on one or several layers, one or several orbits. These orbits are called electron shells, and each shell can contain a certain number of electrons. The first shell can hold up to 2 electrons, the second up to 8, the third up to 18, and so on. For reasons related to energy levels, which we'll leave aside for tonight, atoms like, and I say like in quotation marks, they like to saturate their outer shell because it gives them greater stability. So atoms have a propensity to bond with other atoms and form molecules, because sharing their electrons in pairs gives them this stability. For many molecules, the sharing of electrons between atoms allows each atom to attain the equivalent of a full outer shell. A simple example of this is with hydrogen. Hydrogen is the simplest form of atoms. It has one proton in the nucleus and one electron. Ideally, 2 electrons would be more stable to fill in the first electron shell that can hold 2. So in nature, 2 atoms of hydrogen will tend to bond and form one molecule, where each atom has the equivalent of a full shell. The same happens with oxygen, but atoms of different elements can also bond. It is the structure of their electronic layer that determines their chemical properties. Their propensity to associate or reassociate with other atoms when they are in close contact. But there is another type of bonding between atoms when one atom gives one or several of its electrons to another. For example, let's say one atom has one electron on its second electronic shell that can hold up to 8, and another has 7. They could both benefit in terms of stability from the first atom giving its single outer shell electron to the second one so that they will both have their outer shell complete. But when this happens, the two atoms become electrically charged. The first one now has more proton than electron, and the second one has one additional electron. As we have seen before, they turn into ions. One negative with a negative charge, the other with a positive charge. Due to electromagnetism, they both turn into tiny magnets that are attracted to each other, so they stay stuck to each other. An example of this is sodium chloride, also known as table salt. Sodium and chlorine tend to turn into ions when in contact. Sodium atoms lose an electron and chlorine atoms gain one. They automatically bond because their electric charges become opposite, and this forms table salt. This is a good example of how chemical bonding and the interactions between these tiny electrons can dramatically change the properties of matter. In atmospheric conditions, sodium alone can be dangerous because it is explosive. It spontaneously explodes in the presence of water because it bonds with oxygen, and this releases hydrogen. Chlorine forms a gas in the atmosphere that is very toxic. But the two together create a compound that is perfectly stable and harmless. I mentioned before that even though molecules were very common in our biosphere, this form of grouping between atoms was far from systematic. Actually, most of the matter under our feet, from the crust to the core of the planet, is not made of identifiable molecules. There are other types of chemical bonds. For example, what happens with metals. It is interesting to spend a bit of time on metals because this is another term that has different definitions and they can be confusing. In everyday life, what we call metal is a material that is hard at normal temperature, which can be polished and will look a bit shiny, and it conducts electricity and heat rather well. That includes iron, copper, zinc, gold, silver, and also alloys like steel, which is an alloy of iron and carbon. This is a convenient definition, but not a scientific one, since it mixes up basic elements and compounds that are made of several different elements. And it is also based on room temperature and common conditions of pressure. Metals can also be liquid or gas. if they are heated enough, so their hardness doesn't define them scientifically. So in physics or chemistry, metals are not exactly the same thing, even though there is an overlap in definitions. A metal is defined as a substance capable of conducting electricity at a temperature of absolute zero, the total absence of heat. Based on this definition, the metals I mentioned before, like iron or gold, also are metals in physics or chemistry terms. But elements can become metals under high pressure, even when they are not defined as such at room temperature. For example, iodine, which is a non-metal unless it is exposed to a pressure of 40,000 times atmospheric pressure. When it is, it becomes metallic, and equally, some materials that are metals at atmospheric pressures, like sodium that we mentioned before, become nonmetals. In the case of sodium, it requires pressure of 2 million times atmospheric pressure. Of course, this cannot happen naturally around us, but inside the core of a planet, it can. So metals conduct electricity well. But why is that? As we have seen before, electricity is a movement of particles, especially electrons, and metals are a favorable environment for this movement because they form objects with a lot of free-moving electrons that are not attached to specific atoms. They form what is called metallic bonding, which is a form of chemical bonding in which you have plenty of atoms that are positively charged. They lack electrons that would make them electrically neutral, and these atoms share free electrons to stabilize the structure. So if you take, let's say, a piece of iron, there are no individual molecules inside. It is one single block of atoms bound together by the sharing of their free electrons. The presence of free electrons, this metallic bonding, accounts for many properties of metal, like their strength, their electrical and thermal conductivity. That's why electric wires are made of metal, copper generally. The structure of a metal wire can be pictured as plenty of positively charged atoms, ions held together by an ocean of negative electrons. This is metallic bonding. Now, metals can also exhibit other types of chemical bonding. I mentioned earlier about sodium forming table salt with chlorine, or iron can bond with oxygen. This is what happens when rust appears. But once a metallic bond is formed, the atoms in metal tend to have a strong attractive force between them. Much energy is required to overcome it, and this is why many metals have high boiling points, generally several hundred degrees. So as you see, there are different types of groupings between atoms, and the way they form bonds into much bigger objects with atoms of the same kind, or different kinds, is determined by their electrons. Let's go even smaller and look inside an atom. We are now on a scale far beyond what microscopes can see. As I mentioned before, There are about 30,000 billion cells in the human body. Each cell is made of billions of atoms. It's estimated that the number of atoms in an average person is roughly 7, followed by 27 zeros. In other words, 7 billion, billion, billion. And even though there are dozens of different elements in a human body, only 3 of them, 3 types of atoms, add up to 99% of the total. Hydrogen, which is about 2/3 of the body, oxygen, which is 1/4, and carbon for 1/10. A lot of this is water, hydrogen, and oxygen. But these 3 atoms combine with others into many different types of substances that make up most of our physical bodies. Atoms may be tiny, but they are empty space for the most part. Imagine an atom has the size of a stadium. Then the nucleus would not be bigger than a tennis ball at the center, and the electrons would appear to be very far from it. The space in between is empty. But this is an image because electrons are revolving very fast around it. They form like a cloud around the nucleus. So it may be more accurate to picture the atom as a dense nucleus and a cloud around it, a zone with lower density. What keeps atoms together is the electromagnetic force. This interaction we already talked about. One of the 4 fundamental interactions. Protons are positively charged. Electrons are negatively charged. This is just a convention to describe opposite forces, of course, so they stick together. But except for hydrogen, which has only 1 proton, every nucleus contains several protons. If we follow the logic of electric charge, these protons should repel each other, and the nucleus should be unstable. Yet it remains intact because of another force, one that acts over extremely small distances and is powerful enough to overcome the electromagnetic repulsion. And this force is called the nuclear force. It binds protons and neutrons together, and it makes the nucleus very stable and hard to crack. This nuclear force was considered to be one of the 4 fundamental forces or interactions I mentioned before, the strong interaction. But since the 1970s, it appeared that it was not exactly like this. The nuclear force is a residual effect from a more fundamental force, one that keeps even smaller particles together inside protons and neutrons. And the nuclear force is a side effect, a residual effect of this more fundamental interaction. But it is what keeps the atom's nuclei together. However, all nuclei are not perfectly stable. A big nucleus may fission, which liberates a lot of energy, and this is the mechanism used in nuclear reactors. When they absorb additional neutrons, heavy and unstable atoms like uranium or plutonium become so unstable that they fission into smaller nuclei, or even without fissioning. Nuclei may be subject to something called radioactive decay due to their instability. They lose energy by radiation. The nuclei emit one or more particles or photons, a particular type of particle that has no mass. There are different types of radioactive decay. One of them, beta decay, is caused by the fourth fundamental interaction called the weak force. Everything we have seen before, as we advance from our scale to smaller and smaller levels, was relatively easy to picture because it obeys forces and laws we are familiar with. Mass and gravitation, electric charge, and electromagnetism are concepts we can understand and apply to a small scale in our head. But once we enter the realm of subatomic particles, it becomes much less familiar and close to impossible to picture, because maybe the most important discoveries in physics since the second half of the 20th century are about the exploration of a world where what we thought we knew about matter, based on our sensible experience and the state of science until then, no longer applied to the subatomic scale. In this realm, particles can exist without a mass, which is not easy to accept since we are conditioned to think that any real physical object has to be made of matter, made of something tangible. In this tiny world, particles become unpredictable, and you cannot know where they are. The distinction between energy and matter, or between the wave and a particle, all get blurred. The tools to approach this reality are no longer in our sensible experience and logic, but rather in mathematics and hypotheses that defy our imagination. To approach the physical properties of nature on an atomic and subatomic scale, the best theory or field of investigation we have available at this point is called quantum mechanics or quantum physics. Quantum mechanics is not that recent. It arose gradually, starting a century ago, as a reaction to observations that could not be reconciled with classical physics. Until 1900, scientists had managed to describe many aspects of nature at an ordinary scale. One cornerstone of classical physics, and it remains very useful nowadays, was Newton's theory of gravitation. It worked for bodies on Earth. It seemed to work well for planets and stars too. So from there, it was tempting to extrapolate to all scales and consider that the fundamental laws of physics were already understood. That was very much the consensus by the end of the 19th century. Scientists knew that a lot remained to be explored on a very small or on a very large scale, but the laws that governed matter were not a big concern. Until this comforting feeling began to crumble due to observations that did not correspond with what was expected. The works of scientists like Max Planck, and even more, Albert Einstein, shook the world of physics because they showed that the world was not exactly what it seemed to be. Things that were seen as constants, like the passing of time, were not. There may be more dimensions than the familiar three dimensions of space. Particles did not behave as expected. The distinction between a particle and a wave was blurred. A bit later, radioactivity was discovered, proving that matter and its interactions were much more complex than thought. Quantum physics was born out of the need to explain, or rather to rebuild physics on a very small scale in order to understand how atoms and the particles that make them up behave. It is a field, not a single theory. It is based on a mathematical framework that was developed in 1950 by physicists like Werner Heisenberg or Niels Bohr. The basis of quantum physics, quantum mechanics, and this is where it is not intuitive at all because it contradicts classical physics, are first that certain properties, like the position or the speed of something, do not follow a smooth, continuous spectrum. Instead, properties click from one state, one position, to another. Let's take an example with light and colors. For a long time, it was believed that light was just a wave. 200 years of experiments had shown that light behaved like one, until Max Planck analyzed in detail the distribution of colors emitted by a light bulb. Logically, if light was only a wave, the distribution of colors along the spectrum should be perfectly smooth, with the same gap between each specific color emitted. Planck realized that even though a great number of colors were emitted on the spectrum, there were holes on it. Only combinations of certain colors were emitted. Instead of having colors evenly distributed on a continuous spectrum, this meant that something prevented atoms from producing the colors that should have occupied these gaps. The term was later coined to describe this is quanta, quantized, which gave quantum properties, in that case color, but it applies to other properties like position or speed, which can jump from one set amount to another. Decades later, this intuition was confirmed many times by experiments. Particles may or may not be where we would expect to find them. They may occupy a position and in their next set of properties be somewhere else without consuming time to travel from one point to the next, and yet be somehow connected to other particles. This defies imagination, but a metaphor to try to picture it is imagine a dial. Properties click like a dial that changes settings. Another fundamental principle is that light can sometimes behave as a particle, one that has no mass and matter, despite having a mass, can also behave as a wave. Within the field of quantum physics, different theories explain the fundamental forces by which matter interacts that we have talked about before. Electromagnetism, that explains how atoms hold together. the strong nuclear force that explains how the nucleus remains stable, or the weak nuclear force that explains why radioactive decay occurs to some atoms. At this point, the various theories that explain these forces have been regrouped under an umbrella called the Standard Model. This model explains three of the four fundamental interactions. The fourth one that is out of the field, at least for now, is gravitation. That appears on a macroscopic scale, not at the atomic level. The Standard Model describes a lot of different elementary particles, matter particles, also known as fermions, like leptons and quarks, that come in 6 different types each, and the force carriers, also known as bosons. One major challenge is to unify these theories that are connected by their principles, but do not form a single theory of matter, and maybe one day reconcile them with gravitation, because they do not explain this force nor connect it to their description of the infinitely small. However, the Standard Model has been vindicated several times over the past 3 decades with the discovery of particles that had been predicted theoretically but never observed before. Their presence could be proven through experiments in particle accelerators. The one discovery that garnered a lot of attention in the media was the Higgs boson in 2012. It had been predicted in the 1960s as a particle that gives all other particles their mass, and the fact that it was attested 50 years later shows that quantum mechanics is a powerful field. It works. But quantum physics remains very hard to present to the public because it makes predictions. It anticipates things about matter that seem to be completely at odds with how things seem to work in the world we experience. It says that particles can either be located in a single place, or they can act like waves and be distributed all over space, or in several spaces at once. How particles appear to us depend on how we choose to measure them, which questions the nature of reality itself. Is it something independent from our perception? Our measurement of it? Also puzzling is the fact that quantum particles seem to be able to affect each other, even when they are far away, and we ignore how this is even possible. This seems so far from what we know of reality or how we experience it, that maybe there will be a more intuitive theory one day that remains to be formulated that could better unify and explain these forces and these observations, like Einstein did when he explained gravitation with his second theory of relativity. Maybe like Einstein did with the concept of space-time and its curvature, there could be a concept that would embrace all these elementary particles and their interactions. This is certainly the holy grail of physics at this point. This is where our journey ends to the infinitely small. I hope you enjoyed our time together. You may now let go and sleep, or if you're not sleepy yet, you may pick another story from my ever-growing library. And until we meet again, Good night. Sleep well.